Okay, guys, I wanted to work out one of the worksheets for you so that you'll kind of have some examples to follow. So I'm going to do the Chapter 7 extra practice for you, and you should complete the Chapter 7 class practice worksheet for homework. I found that that one was a little bit simpler, so that'll be the one that will be graded as a homework grade. But we'll go ahead and have you guys turn in both worksheets. That way you'll have 2 different daily grades. So make sure you complete the Chapter 7 extra practice worksheet as well. Sorry, but as you watch the video, I'll complete it with you here. And then you'll need to do the Chapter 7 class practice worksheet, and then you'll need to do the textbook assignment that was also assigned. Okay? So number one hospital employs 200 nurses. 75% of all the nurses are female. 55% of all the nurses are under 35 years of age, and 5% of all nurses are male and 35 years or older. Part A, make a two-way table or Venn diagram classifying nurses by gender and age. I found that doing the two-way table was easier for this problem. So we have males and females, and then we have either under 35 years of age or over 35 years of age. So when I created it, I did females just because that's what they talked about first. And then I did males. And we want to do under 35. Sorry, my alignment's not the best, and then over 35, okay? And so we have given to us 200 nurses, 75% are female. So I'm going to do 0.75 times the 200, and so that gives me a total number of females of 150. So the entire female column should add up to 150. Okay, proceeding on, they say that 55% of all the nurses are under 35 years old. So I'm going to do 0.55 of 200. That's 55% of 200. So 110 is my total for under 35 years old. So under 35 is going to go over here. It's going to be on the row. And again, that's 110 for the total on that one. 5% of all nurses are male and 35 years or older. So I'm going to do 0.05, representing the 5%, times the 200. And so that's 10 people fall into that category. So they're going to be male and 35 or older. And there's 10 of them, so that's going to go here. So that's all the information they give us, but we can figure out all the other pieces from some totals that they gave us. We know that the total is going to be 200 because this is, we have 200 total nurses. So if we have 150 females, then that leaves us with 50 males because you're going to do 200 minus the 150 females, and that gives us that 50 right there. Well, for males, that tells us we have a total of 50, but we have 10 that are over 35, so that would leave us with 40 being under 35, since those two, the two cells, 40 and 10, have to add up to the 50. And then we're going to do, let's see, we have 110 total people under 35, and I know that 40 of them are males, so that would leave me with 70 being females, since 70 and 40 need to add to 110. Backing up a second, if I have 110 under the age of 35, then I'm going to have 90 over the age of 35, since 110 and 90 need to add up to the 200. And then I'm missing a little spot here. I need to know how many females are over the age of 35. A couple of different ways I can get it. I know it's 80 because 70 and 80 have to add to 150 for the females, or I could say 80 plus 10 has to add to the 90 for being over 35. So lots of different places where you could figure out the missing cells. Okay, so part B, find the probability that the person is female and under the age of 35. So female and under the age of 35, there's 70 of them from our first cell there, and you want to take it out of the total, which is 200. And so 70 over 200 simplifies to 7 over 20, and then as a decimal would be 0.35. So you can tell me it's 0.35, you can tell me it's 35%. Any of those answers would be fine. So you could say 7 over 20, you can say 0.35, or you can say 35%. Find the probability that they are male and 35 or older. So male and 35 or older are 10 of the nurses, and we want to go out of the total number of nurses, which is 200. Simplifying that would get you down to 1 over 20. We can divide that out. if we want the decimal answer instead. So that would be 5% or 0.05. So 0.05 are both male and 35 or older, which honestly, they gave you that in the scenario. So it's kind of nice to be able to verify that that is actually true. So our setup must be pretty good. Okay, so moving on, part C. Find the probability that you are male or under 35. Okay, so males, there's 50 of them. Under 35, there's 110. I'm going to add those together, but you have to remember that you just double counted some people. Anybody who was male and under 35, you counted them in both sets. So you need to subtract those people away. So that's the 40 males that are under 35. So I did the 50 total males, the 110 total people that are under 35. But in those, I counted the 40 males that are under 35. I counted them in both groups. So you have to subtract that overlap. So 50 plus 110 minus 40 ends up being 120. But remember, we're doing probability, so we need to take that out of the total of 200. So 120 over 200 can simplify. 120 over 200 simplifies to 3/5. If I divide the top and the bottom both by 4. And then 3/5 would be 60% or 0.6. Okay, so that is it for number 1. Moving on to number 2. 2 dice are rolled. Remember when you roll 2 dice that you are going to have 36 possibilities. So we're going to use that information. We're going to assume we all remember that sample space. Okay. Find the probability of getting a sum of 6. How could I get a sum of 6? I could get a 1 with a 5. I could get a 5 with a 1. I could get a 2 with a 4. I could get a 4 with a 2. I could get a 3 with a 3. So there are 5 possibilities for getting a sum of 6. So I'm going to say it's 5 out of 36. If I want the decimal answer, I'm going to do, let me see if I can get rid of this, go away, 5 out of 36. So 0.1389 would be about 14%, or I'd prefer you to stay with the decimal places, so I'd say about 13.89%. Okay. Part B, we want the probability of getting doubles or a sum of 4 or 6. So the possible doubles we could get 1 with 1, 2 with 2, 3 with 3, 4 with 4, 5 with 5, or 6 with 6. Okay? Sum of 4, I could get 1 with 3, 3 with 1, or 2 with 2. To get 6, I could get 1 with 5, I could get 5 with 1, I could get 2 with 4, or I could get 4 with 2, or I could get 3 with 3. The problem is we have double counted some stuff. So the 2 with the 2, I don't want to count it again. And then the 3 with the 3, I don't want to count it again because it's already been accounted for in the doubles. So for doubles, I have 6 possibilities. For 4, I used to have 3 possibilities, but I'm gonna get rid of the 2 with the 2 because I've already counted it in their doubles. So there's only 2 possibilities for getting a sum of 4. And then for the 6, I'm going to discount, not do the 3 with the 3. So there's only 4 possibilities. So I have 6 plus 2 plus 4. So that gives me a total of 12 possibilities. But remember, it's out of the total 36 possibilities, so it's 1/3 or 0.3333. So we would say it's about 33.33%. Okay, so about 33%. Number 3, if a student guesses on all 5 questions on a true-false exam, find the probability that he or she will get them all wrong. The probability of getting them all wrong, getting one wrong even, would be 1/2. If it's true-false, then half the time you guess and get it right, half the time you guess and get it wrong. Okay, because there's only 2 possible answers. But you have 5 questions. So on the first questions, I have a 1/2 probability. On the second question, I have a 1/2 probability. On the third question, I have a 1/2 probability. On the fourth question, 1/2 probability. And on the fifth question, 1/2 probability. So to make it shorter for myself, I would just do 1/2 to the 5th power. And so when you multiply that out, I would do 1/2. Raise it to the 5th power, and as a fraction, that's 1/32, okay? But as a decimal, let's see what that would be. If we did 1 divided by 32, I also could represent it as 0.0313. So about 3% of the time that would happen. Okay, 26% of all deaths are caused by heart disease. If 3 randomly selected deaths are chosen, what is the probability that they all died from heart disease? So you want, the first person, 26% chance they died of heart disease. Second person, 26% chance they died of heart disease. Third person, 26% chance of dying of heart disease. But I want to multiply those together because it's not or. You want all 3 people all died from heart disease. So if all 3 things have to happen, then it's first person and second person and third person. So we are going to want to multiply. And to do it quick in the calculator for ourselves, let's just take 0.26 and raise it to the 3rd power. A lot less to have to type in. So that gives us that beautiful decimal answer there. I would shorten it to 0.0176 personally. So not even 2% of people. You move that decimal 2 places to the right, so it's actually 1.76% of people, so not even 2%. Okay? Number 5, use a conditional probability formula to solve the following. 33% of all registered voters are Republican. 97% of Republicans believe in God. What percent of registered voters believe in God and are Republican? So I just did percentage that believe in God would be 0.97, and then percentage that are Republican would be 0.33, and we multiply those together and we get 0.3201, so about 32%. Number 6, if a day of the week and a month of the year are each randomly selected, what is the probability of picking Friday and February? So picking Friday has a 1 out of 7 chance of happening because you're just picking a random day of the week. Picking February has a 1 out of 12 chance of happening because you're picking one of the months. You want them both to happen because this is and, so you are multiplying. So that ends up being 1 out of 84 when you do 1/7 times 1/12. So if we write that as a decimal, you should get 0.0119. So for time's sake, I'm not going to sit here and type every single one in the calculator, but you could do on the calculator 1/7 times 1/12, and you would get the 0.0119. Number 7, a box contains 12 batteries, 3 of which are defective. Sorry about that. If 2 batteries are chosen at random, find the probability that they are both defective if the first selection is replaced before the second selection is made. We want the probability they're both defective. So we're going to get 3/12 the very first time we go into the box and grab a battery. 3 out of the 12 are defective. We put it back, and so the second probability is still 3/12. We want both of them to be defective, so therefore we are going to multiply those together. So 3/12 times 3/12, let's see, I got to find it on my notes here, would be 1/16 once it is simplified, because you're going to do 9 over 144, and then you are going to simplify that. If you did it as a decimal, would be 0.0625. So please, guys, go through and calculate these on your calculator to double check where I'm getting these numbers from, okay? Part B, the first selection is not replaced before the second selection is made. So we start off again with 3/12 when we go in the box for getting a defective battery. But we assume that the first battery we got was defective. And so when we go in that second time, now there's only 2 defective batteries and only a total of 11. Because remember, I've taken 1 out. So that would be 6 over 132 when I multiply that. And then that would simplify to 1 over 22. As a decimal, we would give the answer 0.0455. So about 4.5% of the time. Okay. Number 8, 62% of TCW students take both math and science. If 85% of the students take math, find the probability that a randomly selected student takes science given that he or she takes math. So we are given that they take math. So when I try to use my formula that we learned for this, I'm going to let B be math, even though they might have talked about it first, because in our formula, the given part is always the B, okay? So the probability or the, whatever, the event that they take science, that should be our A event. And again, I'm doing it that way because they say given they take math. And our formula says the probability of A given B is equal to the probability of A, sorry, see if I can erase that, probability of A and B on the top divided by just the probability of B on the bottom. So probability of A and B would be the probability that they take both. And it says 62% of students do that. So that would be 0.62 on the top. And then on the bottom, it's just the probability that they take math, which the scenario tells us is 0.85 or 85%. So we would divide 0.62 by 0.85 on our calculator. I will go ahead and type that in for you. 0.62 divided by 0.85. And so you have a final probability of about 73%. So we've got 0.7294. And so you get about 73%. Okay. 85% of TCW students take math and 72% take science. If 62% of the students take both math and science, find the probability that a randomly selected student takes math or science. So you can kind of start off with the defining your events again. So like A, I'm just going to let it be math. This time I don't really care the order that I put it in because it's not a given problem. Okay, so it really doesn't matter which one is A and which one is B. What I do know is I'm trying to do OR. So I'm going to do the probability of A or B, and I need to remember that that's equal to adding the individual probabilities together, but I have to remember to subtract the overlaps. We need to subtract the probability of A and B because you've already accounted for it twice when you do A and B separately. So you do need to subtract one of those out. So the probability of A is 0.72. Let's see, is that right? Let's see. A is math, B is science. I have the probability of A taking math is actually 85%. That's right from the beginning. 85% take math. So sorry, that one's going to be 0.85. And then the probability, I let B be science this time, so 72% take science. So I'm going to let that be 0.72. Taking both, they gave us to be 62%. So that's the part that I need to go ahead and subtract on the end. So we are going to do 0.85 plus 0.72, and then subtract the 0.62. And so we end up with 0.95. There's a probability of A or B happening 0.95, or 95% of the time. You could also do a Venn diagram really quick. I'll show you what I did, like super fast. I did 0.62 in the middle. That's the overlap. Always start with the overlap. And then if this is math on this side and this is science on this side, to get the side of math, and I really need bigger circles so y'all can see those numbers. Let me erase that and try again. I really don't like writing on the smartboard. Sorry, guys. Probably still not leaving myself enough room. This is 0.62. The entire math has to be 0.85, so that leaves you with 0.23 for this side. So remember, the 0.23 and the 0.62 have to add to 85%. So that's why I'm putting a 0.23 over there. And then the science is 72%, so that leaves me with 0.10 for this side over here. So if I did it with a Venn diagram, and I would have you know, the outside piece, which ends up being 0.05 if you do it correctly. But anyway, if I did it with the Venn diagram, I would just do 0.23 plus 0.62 plus 0.10. And that should also give me the 0.95. So either way, you should get the same answer if you draw the Venn diagram correctly. Okay, we are now on number 10. A box contains 12 batteries, 9 are working, 3 are defective. If you randomly select 2 batteries, what is the probability that 1 works and 1 is defective? Either order is possible. This one's kind of tricky. Let me actually give myself a little bit more room to write. Nope, that's not going to work because you won't be able to see the question. Let me zoom out a little bit. All right, really making a mess. Okay, don't want to do that. Let's see if I zoom back in if it fixes it for me. Probably won't. Oh, there you go. It's great, Miss Hall. Good job. Y'all are very used to me doing this in class, so I'm sure this is not bothering you at all. But I cannot, for some reason, get this to be in a way that it'll line up my ink again and stop doing that. Give me another minute. Sorry, guys. So I guess maybe at this point I can just erase stuff and see if I can go from there. All right. Sorry, totally struggling with the smartboard issues right now, but maybe maybe I can do it from here. Okay, I'll quit messing with it and just go from here. So I can, again, I want one defective and one to be good is the way I'm reading it. One works and one is defective. So there's different ways of me getting that. I could get the first battery working and the second battery defective, or I could get the first battery defective and the second battery working. So I'm going to add those possibilities together because it's one or the other is going to happen. So the probability of me drawing the very first one to be working is 9 out of 12. If I draw the first one and it's working, then that only leaves 11 batteries in the box, but 3 of them are still defective because I picked one of the ones that's working. So the second probability would be 3 out of 11. Or I go in the box and the very first time I pick a defective one. So that's 3 out of the 12 are defective. And I go in the second time and now there's still 9 working, but there's only 11 batteries in the box. That is the setup for this problem. You can just use your calculator to figure it out. So I'm going to use my fraction button, alpha y equals, I love it. Gives you your fraction button, so you have 9 over 12. And then times the fraction 3 over 11. So that, again, is the probability of getting a working one and then a defective one. So, or the other possibility is that I could get a defective one first. So I'm going to go 3 out of 12 and then get a working one my second time. So times the probability of getting a working one the second time would be 9 out of 11. So that gives me 9 out of 22. Convert that to decimal. I could also call that about 41% of the time. So I would accept the answers 9 over 22 for this problem, or 0.4091, about 41% of the time. Okay. Number 11, make a two-way table of the information. We have a statistics class contains 6 males and 8 females. 3 of the females are psychology majors, while the remaining females are sociology majors. 5 of the males are psychology majors, while the other male is a sociology major. Ooh, that's a lot. Okay, so they give us some random little table down there. It doesn't really go with B, it actually goes with A. So make a two-way table of the information. We have males and we have females. Okay, and then we have psychology and we have sociology. So I'm just going to let this be psych and this be soc. This is answering part A though. Okay, so where did I start? A statistics class contains 6 males and 8 females. So my male column should add to 6. My female column should add to 8. So I must have 14 total students in the class. Hopefully that makes sense. Sorry, guys. And then from there, drop in the markers. We're good. Erase this little extra line. Okay, so 3 of the females are psychology majors. So 3 of the females are psychology. So if 3 are psychology, then that means 5 have to be sociology since it has to add to 8. Okay, and then 5 of the males are psychology. 5 of the males are psychology, so 1 has to be sociology since it has to add to 6. So that means we have 8 total psychology people, and we have 6 total sociology people because you're adding the rows together. So now we have all the information for our two-way table. Part B says find the probability of selecting one student at random who is female, or sociology. So female total would be 8, sociology total would be 6, but it's not 14. I mean, that would give us 14 out of 14. You can't do that because you've got some overlap. So you've got to subtract the overlap. So we look at who is female and sociology. That's 5 people that are 5, females that we have to subtract away that was in the overlap. So 14 minus 5 would be, what is that, 9? And so 9 out of 14 would be the probability of getting a female or a sociology major. So 9 out of 14 as a decimal would be 0.6429. So it's going to be about 64% of the time. Okay. Part C, given that the student is a psychology major, we're given something. We don't even consider the sociology people because it's given that they're psychology. So we only have 8 people we're going out of. I can start right there. It's only out of 8 because sociology doesn't even exist anymore. Find the probability that the student is a male. So it's 5 out of the 8. Okay, 5 out of the 8. would simplify to 0.625. So 62.5%. Okay, fill in the numerical values for the Venn diagram. They're only giving us females and sociology. So we have we have 5 in our overlap because we have 5 females that take sociology, okay? But we have a total of 8 females, so that would leave 3 over here on the female side because we want the female circle to add to 8. Sociology's total is 6, so that must mean that 1 goes over here off to the side because you want the entire sociology circle to add to 6. So that represents 9 of the students, so that leaves 5 students out there because there's a total of 14 students in our entire sample space. Excuse me, that leaves 5 out there in the gray space. So part E says, describe what the shaded region represents in terms of females and sociology. A lot of us would want to say, oh, that's the 5 males that take psychology. And we're correct, but it says you have to do it in terms of females and sociology. So the gray shaded region are the statistics students who are not female and are not taking sociology. Okay, so that's, I'm not going to write the whole sentence out for you, but that's what you would say. You would say it's the not, they're not females and they're not taking sociology. That's what the gray represents. Okay, number 12. We're almost done, guys. A certain test for the HIV has a 20% false positive rate and a 5% false negative rate. For Washington, D.C., 5% of all adults have HIV. Because screening can be expensive, this particular test is used first because it is cheaper. Find the probability that a person who tests positive actually has HIV. I find this problem to be simpler if I look at it in a tree diagram. So I'm going to start off my tree diagram with either having HIV or not having HIV. So 5% of all people in Washington, D.C. have HIV, so that means that 95% of people in Washington do not have HIV, okay, not HIV. Sorry, my alignment on the board's really, really bad, so that's hard to read. It's writing where I don't intend for it to write. Sorry about that. But hopefully you're following me. So HIV is 5%, not having HIV is 95%. So if I take this one test, I get, it says a 20% false positive. Well, 5% of people are positive. So a false positive, that 20%, would not go with the HIV. It would go with the not HIV. Let's think about that a second. If you're false positive, then you don't have HIV, but you're testing positive. So that happens 20% of the time. So 80% of the time, you don't have HIV and your test comes out negative, and that's good. Okay. The other thing is you get a 5% false negative. False negative. So that means that I have it, but the test comes out negative 5% of the time. So positive, negative. I have it though, so a false negative, 5% would go here, 95% would go here, because remember the branch has to add to 100% or 1. Okay, so then you multiply across the branches to get the combined probability, if you will. So we would do 0.05 times 0.95, and it's going to be my first number. And then I'm going to do 0.05 times 0.05. Okay, so I've got 0.0475 here, or I could write that as 4.75%, same thing. And then I've got 0.0025, which is just 0.25%. Okay, then the next set of branches, I'm going to do 0.95 times 0.2, and then I'm going to do 0.95 times 0.8. Okay, so this one is 0.19 or 19%, and then this bottom one is 0.76 or 76%. So that represents our tree, and we can double check it. If you add the decimals together, it does add to 1. If you add the percents together, it does add to 100%. So I got it. It says find the probability that a person who tests positive actually has HIV. So we're going out of people who test positive. So on the bottom of our probability fraction, we want to get everybody who tests positive, their probability. So I'm going to do the 4.75 or the 0.0475, we'll go with that. And we also want to add in the 0.19. That's everybody who tested positive. Sorry, it's 0.0475. So we're going to do 0.0475 plus the 0.19. And then we want only the people who test positive who actually have it. So that is the 0.0475 only. Okay, so I'm actually going to clear my screen real quick, do my fraction button. On the top, I want 0.0475, but on the bottom, I want the 0.0475 plus the 0.19, because the plus 0.19, the 0.19, they actually tested positive as well. They just didn't have it. Okay, so that would be 0.2. If you wanted to write it as a fraction, would be 1/5. So I would accept 0.2, or I would accept the 1/5 as well, if you meant to do it as a fraction, sorry. If you like to give all your answers in fraction form, because I will accept either one. So 1/5, 0.2, or 20% would be acceptable answers. I am going to have to erase my tree diagram so we can look at these last ones real quick. Boy, is this fun, getting all the pieces. Let's see. Okay, I think I got most of it out of the way for us. So, determine which of the following could be a probability distribution. If it is not, explain why not. 13 and 14, neither one of them are probability distributions. They could not be one. Your main thing to check is, does the probability add to 1? Remember, if you have the whole sample space, then the probability has to add to 1. On number 13, if I do 2, 4, 6, 5, 6, 7, so this adds up, I don't know why I just did it that way, 2, 4, 6, and then 7, 8, 9. If you add these together, it's only 90%. It is 0.9. So this one does not work because the probability does not add to 1. If you do the same thing to number 14, you do have the probability add up to 1. The only thing that makes it not possible is you are not allowed to have negative probabilities. So with the second one, we'd say, nope, that's not a probability distribution either, because you cannot have negative probabilities. Okay, number 15, we need to use the fact that the probabilities have to add to 1. And so we do 1 minus the sum of everything we have. So we're going to take 0.125 plus 0.375 plus 0.125. Again, add it all together, subtract it from 1, and you're left with 0.375 for the missing probability. 0.375 would be our K there. And then it would add up to 1. Okay, number 16, a little bit trickier. We have 2 Ks, but we know they're going to be the same because it's the same variable. So I can add what I have. I have 0.3 and 0.4. So I already have 0.7 or 70% of the probability represented. So if I have 70% represented, then I have 30% left over for those 2 Ks to share. So if I have 30% left over, then each one is going to be 15%. So that would be 0.15 and 0.15. And so you want to double check it. It does add up to the 1%. So I hope this helped you guys with looking at some different examples and kind of understanding it. So again, now you need to go and do the Chapter 7 class practice worksheet by yourself, which again, I found it to be a little bit easier than this one. So I'm hoping that you don't have any trouble doing it for homework. And then also don't forget to do the textbook problems as well.